My name is Guy Davidson. I am the Principal Coding Manager at Creative Assembly, which is a game studio based in England. I think we're the largest game studio in England. We make the Total War franchise. We've also made Alien Isolation. That was quite popular. Halo Wars 2. Oh, thank you. Thank you. Halo Wars 2. I've been in games for years. But I love it. Even as a 50-year-old man, I still play games. I'm 51 on Friday. I'll still be playing games. Today I want to talk to you about io2d, which is the reference implementation of a paper which proposes the addition of 2D graphics to the standard library. So this is what we'll be going through. You'll find out. Let's start with life. So this is Conway's Life. Who's written Conway's Life? Yeah, it's quite common. It's a good starting place for writing things. This is written entirely in io2d. There's no platform-specific code here. It's about 200 lines long. Let's start with the main function. So the first thing we do is create an instance of the Game of Life object. And you can see here the first type in the API, which is output surface. And this is the surface that we shall draw to. These parameters identify some of the characteristics of the surface. The first pair is the size of the surface in pixels. And next we have the pixel format, which is alpha, red, green, blue, over 32 bits. Then we have the scaling parameter, which dictates what to do when the back buffer has different dimensions to the display buffer. And we've chosen none here because we know what's going on, but you could choose to stretch or center whilst maintaining aspect ratio, or to tile, or there's all sorts of things you can do. And then we have the refresh style, which is how often do we redraw the back buffer, which is fixed at 30 frames a second. So we declare two callbacks, one for changing the size and one for drawing. Changing size is trivial in this case. We just, change the size, really. The draw callback is going to be called at the refresh rate, which is 30 hertz. This means that we can use it as our model update for updating where all the cells are in the Game of Life, and for our draw update. So having created the window and the two callbacks, we can start things off with begin show. And that's the end of the main function. We don't need to look at the tick function. As I say, most of us have written Conway's Life. It's quite simple. There's a grid with some cells, and as we tick over, sometimes there are cells that get created, some get destroyed, as you see. So let's move straight on to the display function, which does two things. It will draw the grid and then draw the cells. So drawing the grid divides into three parts. We erase the last frame by drawing the background, drawing the vertical dotted lines, and drawing the horizontal dotted lines. Drawing the background is easy. We paint it light grey. Drawing dotted lines requires the use of the stroke function. So let's look at those parameters. We've got a brush, and then we've got a path. We have brush properties. We have stroke properties. Then we've got some dashes and some render properties. And finally, we have clip properties. And you might be looking at those and thinking, what's going on here with all those templates? But there's more on that later. So we can look at these properties individually. So in this case, the brush property is simply a color, grey. So we use a path builder to describe a path, which consists of a set of instructions. So we declare a new figure, then we draw a line down the y-axis, and then we make an interpreted path object out of this. That's our vertical line. The stroke properties consist of a width and a flag for how the line ends, and then the dashes describe the offset and the spread, and the render properties describe how pixels will be blended. And then we put this through a for loop, translate the render target across the board, and then we stroke the dashes. io2d offers linear algebra and geometry maths. To draw the horizontal lines, we simply have to change the path. So we clear the path builder, and then we create a horizontal line, which is the width of the board, and make an interpreted path. Then we put it through a for loop, and we have a grid. And we've covered most of the API now. We've got color, linear algebra, paths, brushes, and surfaces. Everything else is variations on this theme. So let's draw the cells. During the tick function, we calculate the transition point, and we make beta and gamma out of phase. So things are fading in and fading out. So we need a brush for emerging and one for fading, and a brush for simply on. We don't need an off brush. That's a null op. That's what the grey background is for. And finally, for our preparation, we need cell size and a minimum scale, which we'll see in use in a moment. So let's iterate through all the cells with a pair of for loops. I know they're rule loops. I'm sure we can all get over that. We get the state of the cell. It's either on or off or emerging or fading. So we need per cell render properties. Now there are three conditions to deal with. We don't need to do anything if the cell is off. The first condition applies if the cell is on. And here we simply translate to the appropriate position in the grid. And then we call surface fill. So there are 4 drawing operations on the surface. We've already seen stroke and paint. And this is fill. The fourth one is called mask. So let's look at the fill parameters. So the first parameter is a brush. Then we have an interpreted path, brush properties, render properties, and clip properties. So we have a brush, an interpreted path, no brush properties, and the render properties. The interpreted path is a piece of member data. So let's take a look at the constructor. So the constructor initializes the width and height of the board. This is the game of life constructor, just to be absolutely clear. And this is called once at the start of the program. We check those sizes of positive values. So there are 2 vectors, one for the cell state. As you can see, that's cells for the entire board. And then one for the number of neighbors. The way that Conway's life works is that the number of neighbors are counted to see what the new state should be of a particular cell. So the cell figure is a member datum. It's created via an immediately instantiated lambda expression. Terribly modern, terribly trendy. It's just a square. Get a new figure, draw the square, close the figure, return the interpreted path. And that's the first condition, just draw the cell with a black brush. The other 2 conditions are a little more complicated, and this complexity arises from the render properties. What we want to do is shrink and grow the cells as they fade and emerge. And we do this through a series of matrix operations. So first of all, we create a scaling matrix, and then we translate that to the correct offset within the cell so that it remains in the center. And then we translate that to the correct cell before calling fill. And then we do the same thing with the emerging state. And that's the job done. That's Conway's life in 200 lines of client code on the 3 major desktop platforms. Okay, art quiz, who's this? Painted by whom? Painted possibly by Alfred Edward Chalon from 1780 to 1860. There'll be art quizzes throughout to break up the wall of code that I'm going to present you with. So let's look at a bit of history. The technology got here. Well, it's like this is a whirlwind tour of displays and APIs. I usually do this. It's been getting shorter and shorter as time goes on. But displays obviously go back further than cross-platform APIs. If we go back to the very start, the 1950s saw devices like the UNIVAC, which had a form of visual feedback in the shape of lamps that were built into the controller's surface. So this was mixing up the control and the view. Very bad. Displays advanced to cathode ray tubes, which improved matters by shrinking individual element size from big lamps to little pixels. But pixel density was still very low. Bresnam line drawing algorithm. Anyone care to guess when that was first published? 62. Very good, very good. Autumn 62. Vector plotting screens also arrived in the 60s. Anyone know what that is? That's a PDP. That's the PDP-1, in fact. And then the glass teletype appeared. This is displaying a grid of ASCII characters on a cathode ray tube. This was 1963. Look at the aspect ratio. In 1967, logo was created on the PDP. Who knows what logo was written in? Lisp. In the early 70s, the Evans and Sutherland frame buffer appeared, which gave us individually addressable pixels on a cathode ray tube. Setting pixels is all very well, but it's quite remote from the model that we have in our minds of how drawing actually works. We don't think in terms of pixels, we think in terms of lines and curves and things like that. Drawing a line by setting pixels is not trivial, especially if you want to make it smooth and anti-aliased, which is why the Bresenham line algorithm is so significant. The abstraction problem was solved for plotters with the HPGL printer control language. But in 1977, the graphical kernel system was the first ISO standard for low-level computer graphics, finally ratified 8 years later in 1985. It formed the basis of Digital Research's GSX. Anyone use that? I'm really old, aren't I? This consisted of two parts, the GDOS and the GIOS. The former was a selection of drawing routines, and the GIOS was a hardware driver, like a BIOS for graphics hardware. And it was specialized to GEM. Anyone own an Atari ST? Last, thank you. Hi, nice to meet you. So you'll be familiar with GEM. Good, lovely. Wow, okay. That didn't use GEM though, did it? No, okay. So the late 70s saw people like me, this gentleman here, I'm sure, gripped by home computers, which include the Apple for the really well-off. It had a nice frame buffer, and you could connect it to a domestic CRT TV set. Has anyone here never owned a cathode ray tube television set? Ooh. Oh, really? Ah, you're the first person. I always ask this question. There's usually someone says, you know, what do you mean? Of course, I've had a telly. So you've never owned a cathode ray?
I mean, my parents had one when I grew up.
Oh, no, that's not good. You don't, okay. Soon we'll have people who just don't know what cathode ray tubes look like. So meanwhile, IBM Personal Computer, that strolled into town, and that gave us CGA, EGA, and VGA graphics standards. And then PostScript was released in 1984. This rather improved matters. It added font support. And this inspired Display PostScript, which was used on Unix and Next workstations. That was released in 87. Anyone here use Display PostScript? Yay! Okay, we're starting to reach living memory now, aren't we? Not just me. So what happened next? Lots of things, actually. I went to university to study maths and computing. The Berlin Wall fell, and then OpenGL was released by Silicon Graphics in 1992. Yeah, OpenGL is 26 years old. Think on that. Anyone here under 26? So you don't know a world without OpenGL. The last version of OpenGL was released last summer, I think. Microsoft released WinG in September 1994. Anyone use WinG? Yeah, not many of you. It wasn't great. Oh, actually, it didn't set the world alight, but it ran Doom as well as MS-DOS. It was, yeah, I mean, it made a difference. I just don't think people noticed because they were running games on DOS. DirectX, that was released in September 1995. That really sealed the fate of DOS as a gaming platform. 1996 saw the release of the Voodoo Graphics chipset. Finally, 3D hardware could be installed in domestic PCs for extraordinary gaming experiences. They were fantastic. My first memory of this was my friend Jason brought his card round to my house. He put it into my PC and then started up Tomb Raider. And I was engrossed with Tomb Raider at the time, but suddenly, smooth, high-resolution 3D graphics floated across my screen. Although she still didn't look quite right. It was an astonishing step change. So I got to grips with DirectX and OpenGL, and always found them huge beasts when I wanted to do something trivial. So I wrote my own wrapper. I wrote a wrapper library. Lots of us did. Everyone. Has anyone here who's used OpenGL not written a library of utilities to speed things along? That's a bit of a leading question, really, isn't it? But you're familiar with the experience of thinking, that's a lot of API. Some of these wrappers achieve widespread use. Anyone use SDL? Yeah, right, 1998, that first appeared. This offered simpler access to drawing, as well as sound and I/O. GLFW, about 2000. Yeah. Cairo, 2002. Skier, 2005. SMFL, 2007. That's a very popular beast. Or is it? Oh, okay. Which also offered sound and I/O. Cinder, 2010. Yeah, a bit of that. Basically, not a year goes by without someone saying, do you know what? I know what we need. We need a better graphics library. Vulkan. Hello, Vulkan. So, okay, why another library? It's the obvious, it's the elephant in the room, really, isn't it? So io2d was created in response to a call for standardization of drawing in C++ in about 2013. One of the problems with all of these libraries is, really, it's knowing what to choose from. Being certain of maintained libraries for your platform being easily available, and actually installing them on your machine. And that can be problematic in some regulatory environments. There are plenty of code shops that won't allow third-party installations of code, let alone the absence of a package management solution. More on that later. By standardizing a very simple drawing API, C++ can solve some of these problems. And this library has been specified in a paper proposed for publication as a technical specification. A reference software implementation is available on GitHub, and you can see both of these things at io2d.org. Right. Anyone know what this painting's called? Anyone familiar with it? Is it just me? It's just me, isn't it? It's called Beat the Whites with the Red Wedge. It's a piece of Soviet art by this gentleman here, L. Lisitsky. No, that's November 23rd, 1890, not 1980, to December 30th, 1941. So yes, his entire career was laced with the belief that the artist could be an agent for change. Later summarized with his edicts das zielbewusste Schaffen, goal-orientated creation. Right, let's move on to installation. So the reference implementation of io2d relies on third-party software. Originally, io2d was implemented as a modernization of Cairo. So you will need an installation of Cairo. If you're running on OS X, there is also a native implementation which uses core graphics, although you might prefer to use the Cairo implementation. This means you need to get Cairo into your build paths. In addition, you'll need graphics magic, which is a collection of tools and libraries to read, write, and manipulate images in most of the popular file formats. If you want to build all the samples, one of them needs boost. You'll need that. If you're on Linux or OS X, you will also need libpng. On Linux, you'll need a recent GCC, 7 should do. On OS X or iOS, you'll also need CMake. Additionally, on OS X, if you're running Xcode, you'll need to download a fresh version of libc++, until yesterday, when the Mojave update finally included support for std-visit. What a lot of dependencies. Did somebody say package management? But back to the present. There are already a number of package managers available. We've chosen to rely on vcpkg, as it allows us to install all the packages we need for a Windows installation. And again, as of this week, you can now get io2d on vcpkg. I discovered this after this section, so pretend that you can't, just for the full comedic impact of what's about to befall you. On Linux, we use apt. On OS X, we use brew. I'm going to describe the Windows installation process. Linux and OS X installation is also described in the GitHub repository building.md document. So if you aren't familiar with vcpkg, Microsoft sponsors this one. And you can get it at github.com/Microsoft/vcpkg. It supports Windows, OS X, and Linux. Installation is pretty simple. Just run the batch file or the shell script file if you're on OS X or Linux. Once you've got vcpkg installed, you can install Cairo with the command vcpkg install Cairo. This will take a while. Quite a while. Quite a long while. You'll also need to install Graphics Magic for PNG support, which you can do with that command line. Obviously, all of these slides will be available. You can download it from the GitHub. It'll give you instructions on how to do this. But I just need to be sure that you all know what you're letting yourselves in for, should you decide to do so. Once you have Cairo and Graphics Magic in your build paths, you're ready to build io2d. The reference implementation is described through CMake files, and you need to make some choices, 4 to be precise. And then you invoke CMake with a command line that looks something like that. And then you open your solution and you're good to go. I've got to say, it is 2018, and this seems utterly inappropriate. Surely by now, with all the experience we have of truly wretched installations, we can come up with a standard way of describing a library or a binary, what its contents are, how it was built, what the switches were, how it has been, what the options were, all of this stuff. And I think it's important that we solve this problem really quite quickly. When we teach people C++, when we teach newcomers, We've got to minimize the barriers to entry. When we tempt them with interesting things to do, we've got to be able to say, just add this library to your collection and hash include superlib.h. That's how easy it has to be. I've got a young friend back in Brighton. He's learning C++. He's 12 years old. 12. He's hacking on his Game Boy. What an excellent way to learn C++. Or not, as it turns out, because just the amount of time being spent on bureaucracy and on the administration of library management and include paths and things like that. He's 12. He gets bored easily. Actually, he doesn't get bored easily. He's amazing. But still, it's really quite frustrating. Not enough of our time is being spent on actually getting to grips with learning how to write code, of learning how to model abstractions, how to optimize, all that kind of thing. So if you care about this, if you've got great ideas about how to proceed, do join in. There is effort underway on the committee. There's a mailing list for the tooling group. Subscribe, read the history, tell us your new and great ideas because we need them. Rant over. Time for an art quiz. Who painted this? I will award points if anyone knows who painted this. Except to Hannah and David, who already know. Oh, you've forgotten. Oh, yeah. Glad you were paying attention, thank you. It was Nancy Kaminsky. Oh, all right, none of you? Okay, paint along with Nancy. Great TV show. Oh, tough crowd. Oh my God. Sprites. Okay, I'm going to try an experiment. I'm going to say a word, and I want you to say the first thing that comes into your head. Okay, ready? Internet. What? Cats, yes. Correct answer is cats. The internet is a series of tubes filled with cats, I'm told. So the theme of the next demo is sprites. Let's see it running. There we are. Lots of lovely kitties. So this demo is a little short of 190 lines. It covers a few interesting corners of the API. Sprites, cats. Anyone here got any cats? Yeah, I love cats. Right, let's start with the main function. We start by loading a cat picture. Well, obviously. Then we get its size, and we create a brush from this image. And then we create an output surface. And next we have a vector of cats. How heavenly. And a target number of cats to be displaying. We'll stick with 15, but I'm sure they'd like more. So now we have the draw callback. So the first thing we do is remove cats that have become invisible. Here's a lambda for detecting that, if only real life were so useful. So we have erase remove if for the win. And then we replace them with new cats. And then we erase the surface by overpainting it in dark grey. And then we animate. And then we draw each cat. And that's the end of the lambda at the bottom. So we attach that callback to the surface, along with a trivial size change callback and call begin show. So we have three functions to look at: is visible, spawn cat, and draw. So let's look at spawn cat first. We make some random distributions. And then we create a cat object, initialize it, and you'll see a random animation strategy is being chosen, and a random Y position, and a random X speed, and a random Y speed. The X position is always 0. We start from the left and carry onwards. And if you look at the source for yourself, you'll see the full set of animation strategies and how the animate function works. It does with the stretching and the rotating and spinning and the hypnotic effects, just like real cats. Is visible is simple. So we create a bounding box, which is the size of the surface, and a simple lambda, which tests whether a point is within this bounding box. And then we transform the input according to its animation strategy. And then we invoke that lambda on the corners of the transformed input. And if any of them are true, then the cat is visible. So this is a simple piece of geometry, possibly another standardization candidate. Let's look at draw. So first we check that the cat is worth drawing. Is it actually... No, I mean... This isn't a value judgment. Is it? Actually, it is a value judgment. Is it big enough to actually register as a pixel? If it gets too small, there's no point in adding it to the drawing burden. So this is just a simple cut. And actually, this could have been done in the invisible function, but there's a difference between being visible and being worth drawing. but it would execute faster, being able to cull earlier. Decisions. It's just a demo. Next, we create a transformation matrix informed by the animation strategy for the cat. And now we make a fast filter. This is because we care very little about the result of blending pixels. You'll recall that there are sprites tumbling over one another, so that means we're painting pixels, the same pixel time and again. We could choose from good, best, nearest, or bilinear. We don't care. We're putting cats on the screen. That's plenty. Then we create a render properties object, and we set the surface matrix to the transformation. And finally, we make clip properties. So these deal with reaching the edge of the surface and ensuring that only what is necessary is drawn. And so armed with our image, our brush properties, our render properties, and our clip properties, we're ready to choose how to put this on screen. So if the image is at full alpha, here's the top line, that is, it's not in the least bit transparent, then it's a simple in-place overdraw. And we tell the render properties that we're compositing from the source, and we paint the image using our properties. Otherwise, we have to call the mask function on the surface. It's the fourth one, the fourth surface function, which takes two additional parameters, a mask brush and mask properties, and the brush reflects the alpha, and we don't have any additional mask properties that we care about. And that's it. That's the whole thing. Who painted this? Finally, hello. Yeah, Bob Ross. That's a picture of him painting. That very picture. Marvelous individual. Right, our next example demonstrates use of drawing for telemetry. Now, for me, this is one of the motivating requirements for a standard drawing library. I often want to measure durations while my code is running, and there's all manner of ways of doing this. I could go out and buy a telemetry solution for hundreds of pounds from Intel, for example, or I could just put a graph up on screen. But they tend to be convoluted, all of these things. It involves third-party software or connecting to other processes, or, life's too short. So this example profiles the use of the CPU. So let's take a look at it running. I should have made it scroll a little bit faster, shouldn't I? All right, what you can see there, though, is 4 cores on this laptop. Bit of a spike at the front. We've got a gradient going from green to yellow through to red at the top. 2 of the cores are quite busy. I don't know what they're doing. Bitcoin, running this program, probably, actually. So let's take a look at the code. The author here, and by the way, most of these samples were written by people who are interested in library and have decided to have a go. I've added them in. This author's taken a slightly different route, but the order of things is very similar. The run function creates an output surface object, attaches a size change callback function, and a draw callback function, which calls update and display, and then calls begin show. The draw callback is on a fixed rate of 30 Hertz, so we update and draw alternately. Quick look at the update function, get some data. Obviously, measuring CPU load is deeply operating system specific. So there's a piece of platform specific code here we're not going to look at. And if we return to the update function, we see that there's a data source object which consumes this data and puts it at the back of a container of samples. So the data is ready, so let's draw it. Let's look carefully at this. The display function calls 4 member functions: draw the background, draw the vertical grid lines, draw the horizontal grid lines, and finally draw the graphs themselves. So drawing the background is as trivial as you might imagine by now. Is anyone even remotely surprised by that line of code? Well, no, you're not. Oh, okay. You jest with me, sir. How very jolly to have you here. Can you work out the type member datum, the then background fill, perhaps? Brush, yes. It's that simple. Really, there are no trick questions here, apart from the art quizzes. So drawing the vertical grid lines, I would hope, is reminiscent of the life example. We create a new path, start a new figure, draw vertical lines and match the dimensions of the surface, then create an interpreted path from it. And then at 10 pixel intervals along the x-axis, we translate it to the correct offset and stroke it. And let's look at this stroke call. 3 of the parameters are member data. They're default initialized, so there is just a single reusable instantiation. We just create it once. And the same is true of the background as well. mBackground fill is a brush in Alice Blue created in the constructor. The horizontal grid lines are slightly more involved. because we want to partition the surface according to the number of cores. But the process is similar though. Create a new figure, draw a horizontal line to match the dimensions of the surface, and then create an interpreted path from it. And then for each CPU, translate it according to the height of the surface and the number of cores, and stroke it. So finally, let's look at the actual drawing of the graphs. Here's the meaty part of this presentation. There are two things we want to do here. Draw the contour line of the performance, and then fill in the area under the curve. Particularly, we want a gradient from green to red, which sounds like a job for a brush. So one of the member data is a brush called mFillBrush, which is default initialized with a fairly involved parameter list. Looking at the parameters in turn, the first parameter is a point, so is the second parameter. So this is a range from 0 to 1 in the y-axis. Remember, it went from green to red. And next we have an initializer list of 3 gradient stops. Now the gradient stops are a point used in describing a gradient. We want a gradient with a beginning, a middle, and an end. So the beginning is green, so we have the tuple 0 green. The middle, or more precisely 40%, is yellow, and we have a tuple 0.4 yellow. And finally, the end is red, so we use the tuple 1 red. So this will yield a linear gradient from the x-axis to the top of the y-axis, and more precisely, the top of each CPU section. And this is one of 4 types of brush. We have a solid color as well, and a radial gradient, sunburst kind of thing, and a pixel map, or a sprite. The other brush we will use for this operation is the contour brush, which is just a solid color. So armed with all of this, let's look at the code. First of all, we cache the number of CPUs, the size of the surface, and the height per CPU. And then we loop through each CPU. For each CPU, we build the contour. We start a new figure at the bottom of the CPU section, and then we draw a line to each sample point. And then a line back to the bottom of the CPU section. Here comes the clever bit. That's our contour, but we take a copy of that for our contour, and then we carry on initializing for the filled area, where we draw a line back to where we started and close the figure. So we create our brush properties, and our contour is our line, and the graph is the area. So we fill the graph, and then we stroke the contour. That's it. Any guesses? Pardon? No? Sorry? Oh, okay. Oh, no. Right. Masaccio, born Tommaso di Ser Giovanni di Simone, December 1401, summer 1428. One of the first artists to use linear perspective. That's why I put him in there. Very significant. Couldn't find a photo of him. Internet. It's not what it's cracked up to be. Lots of gaps. It's full of cats. Yes, the cats ate the photo, didn't they? That's what it is. Right. So far, so good. Let's try something a little more demanding. Now, I last presented this library in June to the committee in Rapperswil. So let's take a look at this. That is a map of Rapperswil drawn with this library. So we're going to go through, and I'm going to tell you how that worked. So this is quite a long, strap in. We're just going to do this. So this is 750 lines of code, helped by Boost and a bit of networking. So first we get our bounding box coordinates, and we fetch the map data to a vector of bytes. We build a model from that data and a render from that model. Now we create an output surface, a trivial size change callback again, and a draw callback. There isn't any interaction going on here, we're just generating an image. It's all decided at startup, so the draw callback is simply to display the render. And we call begin show. So fetch OpenStreetMap data is a simple use of Boost ASIO and Boost Beast. We go to port 443 of api.openstreetmap.org and we send the appropriate API string. I'm not going to go into the download function. Worth looking at. It's a simple demonstration of the Boost networking libraries, not especially relevant here. So now we build the model. I won't delve into this. Most of the detail is parsing the XML file that we've just received. This detail contains roads, land use zones, pathways, railways, buildings, bodies of water, and leisure areas, which is an unusual name. One of the nice things about Rapperswil, besides being gorgeous in many respects, anyone been to Rapperswil? It's lovely. Oh, you're all on the committee too, aren't you? Ah, that's why. Right, yes. Only committee people. Maybe Rapperswil only exists for the committee. Maybe it's a special, beautiful place that only the committee can go to when things get to... Anyway. But it really exercises the Open Map API. Let's take another look at this map. You can see railways, roads, buildings. It's all there. Okay. Having turned the XML data into a model, let's render it. So we have a render class with a constructor and a single public function. And the rest is helper functions and member data. We'll look at those first. So the private functions draw individual parts of the map. Buildings, highways, railways, leisure areas, water, and land use types. Also, we see some initializer functions which build road representations and build land use brushes. And finally, we have functions for turning ways and outlines into interpreted paths. The member data is largely brushes and stroke properties with a dash for railways. Quite a lot of this. The roads are represented as a black brush with dashes. Different road types have different representations, and different land use types use different brushes. And that's the end of the class definition. Fortunately, the function definitions are quite simple. I hope that by now you can guess what the makeup of these functions is going to be. So let's take a quick spin through these. Let's look at the display function. We create a scaling factor based on the minimum x or y dimension, and we convert that into a meters per pixel value, and also for scaling and translating matrix. And we erase the background and do a lot of drawing. Let's move on to path from way. This creates an interpreted path from a way, a railway or a road. So we have an early exit. So we cache the node data. Here's our path. And here we come across M matrix, which is the presentation matrix, scaled and translated for the display. We create a new figure from the beginning of the way, iterate through the vertices, drawing lines from point to point, and return the interpreted path. Path from MP is very similar. It's used for drawing things like building outlines. So these may have two paths, for example, if the building has a courtyard. But as you can see, it's very much like the previous function. Cache the nodes, cache the ways, create a path, apply the translation matrix, and then we have a commit lambda. Early out, new figure, iterate through the nodes, draw the line, and close the figure. Are we getting the pattern here? Then we apply that lambda to the ways and return the interpreted path. So this just leaves us with the draw functions. Let's start with draw buildings. We iterate through all the buildings in the model. We get the polygonal path of that building, then we fill the path and stroke it. You can see the pre-calculated brushes and stroke properties here. Okay, just a reminder, that's what we're trying to build. Not too tricky. Draw highways. We get the ways, iterate through the roads, and then we look for the road representation from the road type. And if we find it, we get the way, the width, and then we can build the stroke properties, and finally we stroke. Draw railways, get the ways, iterate through the railways, extract the way from the set, create a path from it, stroke the outer path and the inner dashes. So you can see, you can probably identify the railways on this map now from that description, I hope, or I've been wasting my time. Okay, draw leisure. Iterate through the leisures, get the path, fill, stroke. Draw water. I really hope you're getting this now. No outline required, the water is just blue. So we just fill to a path. Draw land uses, clear. Iterate through the land uses, see if we can find the type, and fill if so. That's it, map of Rapperswil. Okay, who's this? Would you like a clue? Who painted that? Van Gogh. Van Gogh. Van Gogh? Huh?
It's Gogh.
It's Gogh, yes. I'm from Britain, it's Gogh. Okay, final demo is a game. Particularly, this is an Asteroids clone. Let's start it up and take a look. Yeah, all right. Didn't say I was good at games. Yeah, it's not quite finished. This was released by Atari in November 1979, the year after Space Invaders. It was a simple vector-based game. It soaked up many of my coins. It's a very simple game. It's actually my go-to tester game for trying out a drawing API. And it was after writing this game for io2d that I decided to pitch in and see if I could help. Much of the standard is built like this. You look at papers and you see how they can be improved. And then you make recommendations to the authors and so on. Lather, rinse, repeat. I offered sufficient help for the original author to make me a co-author. And suddenly I was, come on. Suddenly I was attending committee meetings and championing the paper and generally having a whale of a time. It's that easy. Do get involved with the committee. We need expertise. Speaking of improving proposals, being a video game, there is a need for user interaction. I need to read keys in the form of controller input. It's an upcoming feature of this library, not here yet, real soon now. Dave?
Working on it.
Working on it, good, excellent. So until then, I've got to resort to platform-specific code. Okay. However, on the Windows version, this is a mere 13 lines of source. Well, on the OS X version, there are 7 lines. And there are 1,130 lines of code in total, so I thought this is an acceptable specialization. Any game developers here? Great. This will be right up your street. Right. Starting from the entry points, we create a game instance, then an output surface instance, attach a draw callback, and call begin show. Any surprises here? Good. Right, the game constructor features a fair whack of initialization. Nothing of particular note, although the physics member might look a little convoluted. There's some random number generation, and there's a finite state machine lurking in there as well. Let's look at the update function. I don't know why I templated this over the surface. I haven't actually spruced up the code base for this conference. This is as I wrote it one evening 18 months ago. So there are actually plenty of oddities in here, but I decided I'd leave them in because they're instructive. It's all very well showing you optimal ways of doing things. But sometimes you need to see poor code to realize good code when you see it. Thank you, CB. So I haven't changed this code much at all since I threw it together, and I'll be highlighting optimization opportunities. So there's a finite state machine cycling here, and the 3 states are new level, new ship, and active. So for a new level, we simply wait the level transition period and then generate a level. And then we change the state. For a new ship, we make sure that in the next 2 seconds, no asteroid is going to hit the point where we create the ship. That would be very unfair otherwise. So we do this with a bit of geometry. We create a shape known as a stadium, and that's the sweep described by the asteroid over a 2-second period. And then we see if it intersects the ship point. There is a little bit of geometry in io2d. There isn't much. There's enough to get by. There's a definition of a rectangle and a circle. We need those for surfaces, because obviously the surfaces are rectangular, and we need it for the radial gradients, because radial gradients are circular. Once we have a standard presentation of geometry via linear algebra, there is scope for expanding the maths offerings of the standard library. Right now, there are some analytical functions, sine, cos, all the trig functions, and since C++17, there are the special functions covering things like beta and Riemann zeta functions. They're fun. Elliptical integrals, Legendre, Laguerre polynomials, all these kinds of things. They were published as a separate ISO standard in 2010 and merged in 2017. There are no geometric functions in the standard because we don't have standard geometry. So I had to write these myself. Again, like I do in nearly every code base I come into contact with. And then we change the game state. Having dealt with these 2 states, we get the key states and make a vector of asteroid destruction objects. And then if the interval has elapsed, we update everything, first the ship, then the missiles, and then the asteroids. And you'll see that we pass that vector of asteroid destruction objects to each of these update functions because the ship or the missiles may actually collide with an asteroid and cause its destruction. We have to deal with that in the model later. If there are no more asteroids to update, if that update asteroid returns false, then it's time for a new level. And finally, we draw everything. There's a very simple Newtonian physics engine in those update functions. I've detailed this in other talks. You can take a look yourself if you like. Don't forget, all the sources available on GitHub. Please do take a look. Tell me what's wrong. Tell me what can be improved. Again, this is all easy to do with the standard geometry API. So let's look at the drawing functions. So there are 4 things to draw. The background, the asteroids, the ship, and the missiles. The background is trivial again. Black this time. The asteroids are a little more interesting. So we check if the asteroid is active. Once it's been destroyed, then it's inactive and it doesn't get considered for interaction. So we create a path builder, start a new figure at the position of the asteroid, offset by the first vertex. And then we iterate through the vertices, close the figure, and stroke it. How could we optimize this? First of all, I'm building the path every cycle. There's absolutely no need to do that. So let's look at the class definition. You'll see 4 static path buffers. There are 4 asteroid shapes in the game, and that describe the vertices. It would be much smarter to have 4 static interpreted paths and a pointer to the chosen path in my individual asteroids. Secondly, I could simply translate the path in the render properties rather than moving it and building. So let's look at the ship's draw function. This has 3 states as well: waiting, active, and exploding. So when the ship is waiting, we don't draw anything. This is for the period between a ship being destroyed and the next ship appearing on screen. When the ship's exploding, nothing happens. I would like to add a simple animation of the ship sort of, grappling apart and fading away. Maybe I'll do it after CppCon in my bountiful spare time. When the ship is active, we create a path builder and start drawing at the ship position offset by the first vertex. Iterate through each vertex, drawing a line, and stroke it. How to optimize this? Well, I should probably close the figure for the sake of precision. And secondly, you might be wondering how I manage orientation. The ship rotates, after all. During the update function, I actually rotate the entire vertex buffer, and I need to do that for collision detection purposes. It wouldn't do to simply blow the ship if it's approximately in the area of an asteroid. It actually has to touch the asteroid. Drawing a line, stroke it. So the missile is trivial. We draw a line between the prior and the current position. And because we're updating so frequently, and the missiles travel at a particular speed, that just appears as a single dot. And that's it. That's the whole game. It's quite simple. It's remarkably compelling, and it's not even finished. I still need to add the flying saucers, limit the number of lives you have, put up the scores. There's all sorts of bits and pieces. Games don't actually need to be immersive, photorealistic, flashy, 3D, VR. They just need to be compelling. Who plays Candy Crush? Come on. More than one of you. I play Candy Crush. I love it. And sprite-based games are actually entirely feasible with this library. I might do Space Invaders next, or a side-scrolling shoot-'em-up, or something like that. I've always loved writing games. It's a very satisfying hobby. It's how I learnt to program. It's very engaging. Who pasted this? Who said that? Yep. Shebang. Vasily Kandinsky, 16th December 1866 to 13th December 1944, credited with painting one of the first recognized truly abstract works. The Nazis hated him. Degenerate, I think they called him. Right, that concludes the practical tour of the API. So the next steps for this library is to accumulate users and example code. That's what I think we need to do. And I hope you've been inspired to do things. If anyone remembers the demo scene of the 80s. No. Yeah? Great. Man, I love you. Thanks for coming. The demo scene in the 80s, people with Atari STs and Commodore Amigas would write programs that were designed for just showing off how brilliant they were at programming the Atari ST or the Commodore Amiga. I think this would be an ideal base for a return to that sort of form. So all samples are welcome. We want to exercise the library with as many likely scenarios as possible and to discover shortcomings. I'm sure they're there. We welcome pull requests to the reference implementation, commentary for improvement, all of these things. This is meant to be a lightweight drawing library, okay? Not a replacement for OpenGL or DirectX or Vulkan or Metal, any of those things. It's easy, light, quick, tiny, tiny, tiny API stuff. The idea is that you should be able to use this for lightweight stuff. And if you need to migrate to specialized code, if you find that it's too lightweight, That's something you can do. Okay, this is a library for the 80%. Another thing you might want to try is writing your own maths library or your own renderer. These parts of the library are actually customization points. So let's take a look at them. io2d.h is the place to start. Here you can see all the types we've been looking at are actually specializations. So brush is in fact basic brush based over default graphics surface, templated over default graphics surfaces. The first two are the default maths and surface types, which are provided by the reference implementation. So we have a Cairo renderer and, oh no, this is the core graphics. So we have the core graphics renderer and core graphics maths implementation. But if you want to write a Vulkan renderer, go for your life. DirectX renderer, do it. OpenGL renderer, yeah, why not? Come to the party. Metal renderer, you can do that. DirectX math library, yep, write one of those. I don't specify what those implementations should be. If you come up with better ones than your vendor might supply, use that. Flog it. You know, NVIDIA, they might come up with a superior renderer. I'll be delighted if they did. That's how they're used. These are actually quite naive reference implementations. They're reference implementations. That's the point of them. And if you can write a better matrix implementation, I mean, really, if you can do better, great, do it. The core graphics implementation on OS X was written entirely without reference to any of the developers. It was written simply by reference to the paper itself. Use the paper to write a renderer. If you're interested in these more advanced topics, do take a look at the specification document. It's sitting at revision 8 until there is further review from the committee. The core graphics implementation was written by Dr. Michael Kazakov. As I say, he just used this document. It's really significant. But you'll need this document for some of the finer detail. You can find it in wg21.link/p0267. Indeed, any paper from the committee can be found by going to wg21 link and entering the number of the paper. Of course, we seek to add text and input in the fullness of time. Michael Kazakov is working on that as well. Text is coming along quite nicely. We've even got emoji. We're quite pleased about that. Ultimately, of course, we are aiming for some kind of standardization. We'd like to see the specification published by ISO as a technical specification. We're considering submission to Boost. We're also seeking submission to package managers. We already have vcpkg covered for Windows. And we're aiming to cover OS X and Linux as well. And we're obviously following the package management discussion closely. There is an argument for dividing the library and putting things like the graphics TS into some kind of blessed ISO package manager. But personally, I want to bring improved interaction to the standard. I want sound and vision for everyone. You know, the next step, though, lies with you. Give the library a spin, try writing from stuff. It's fun. Tell us about it. So thank you. Ask me 2 questions. Okay, questions. Microphones. Hey. Thank you. Matthew, hello.
Yeah, hello, Guy. I have a small question because it seems like a good part of your motivation to actually using and writing this is because you don't have a package manager to install Cairo or whatever on every platform. And that scares me a little because I don't think we should want to standardize stuff just because we don't have a package manager.
No, that's not a motivation. The motivation is that we don't have a standard. At the moment, if you want to use graphics, you've got to make a decision about which library you'd like to use, which for starters, for newcomers, is actually quite a hard thing to do. If I said to my 12-year-old friend, right, which graphics library would you like to use? He'd look at me blankly. What I would like to say is, oh, well, you should use stud : brush and stud : output surface. But at the moment, I've got to direct him to whichever library I think is most appropriate for what he seems to want to do.
Okay, so you would say that the reason the previous attempts have failed is because they were not in the standard.
So like the reason
the 10 previous frameworks graphics library attempts have failed to standardize because they were not actually part of the standard.
Well, I don't think anybody tried to standardize them.
Okay, but that would be the reason why it's not widespread. And none of them have become like the de facto standard.
They solve slightly different problems. Cairo solves a different problem from SFML. GLFW solves a different problem from SDL. They're all trying to do slightly different things. If you want to standardize them, provide a motivation, word them, write the wording, that's the hard bit, and then propose it. The reason why we went with Cairo was because it was battle-worn, it was stable, and it was quite small. It was quite a minimal interface. So it was I wouldn't say it's low-hanging fruit, but it was certainly, get on a stepladder and reach up and you could probably get there.
All right.
Okay.
Thanks for the talk. It was very good.
Thank you.
How is error handling taken care of? Like, do you throw exceptions or
Yeah.
the tough bits?
We have a dual interface. Yeah, don't judge. We have a dual interface at the moment. So we have functions that return error code and others that throw. To be honest, there are not many places in the API where errors are likely to occur. So it's quite thin, but it is a subject of frustration for me. I'm really looking forward to Herb's static exceptions coming in. What I imagine happening is, if this TS does get published, is that by the time it comes around to incorporation, it will have gone through revision. We might get, I'm working on a separate linear algebra paper at the moment, so we pull out the linear algebra from the TS and rebase the TS on the standard with linear algebra, and in the same way we revisit error handling if that changed substantially, which I hope it will.
Okay, good. All right, thank you.
Okay. Any more questions? Ooh, I get to go early. Thank you all for coming.